We're going to use the Born Haber cycle to calculate the enthalpy change or formation of an ionic compound. That's heat of formation for an ionic compound. We need to know what that definition is. We're going to use lattice energy as a cornerstone to build off of. And after that, it's pretty much connected dots. In the end, it's a Hess's law problem in which you add up all the delta H's for all the problems you use, and all those will add up to be the final equation. Sounds kind of wordy. Let's go look at the actual equation. So down at the bottom, we have our goal, and that is to figure out the heat of formation for the production of sodium chloride. Sodium chloride is an ionic compound. All of these Born Haber cycles will be ionic compounds. Now, remember the definition for heat of formation. It's going to be building up 1 mole of the compound, and therefore we can't have a 2:1:2 mole ratio at the bottom. It has to end up producing 1 mole of the ionic compound from elemental forms. Sodium comes as a solid metal. Chlorine comes as a diatomic molecule in a gaseous state. F with the degree symbol up there, that represents heat of formation and under standard reaction conditions. Use the lattice energy equation as a cornerstone to build off of. First of all, none of these numbers you have to memorize in terms of the delta H's. However, the signs you must know in terms of positive or negative. So a lattice energy is the energy involved in forming an ionic compound, 1 mole of an ionic compound from their gaseous ions. So we're going to write an equation in which we have gaseous ions forming the 1 mole of sodium chloride. Okay, so we have the lattice energy equation written above. Again, I said this is like a cornerstone. This is what you put in next, and everything else we just have to match after this. So we have to know the definition. Since lattice energy is the energy of the gaseous ions forming 1 mole of the ionic solid, because at room temperature, ionic compounds are solids. To form the compound, you have to be in a gaseous state and you have to already be an ion. This value will be negative, okay? It will definitely be negative down here, highly negative, in fact. The reason is, one, you're going from a gas to a solid. If you remember our heat curve, right? So if you're going from a gas to a solid, that's going to be highly exothermic. Going across the x-axis that way is exothermic. And when you have free ions like these two guys, and they click together to form a solid ionic compound, that's highly exothermic. So if you add a negative and a negative, you get a big negative, and this will be a very large negative value. Next, well, we start with reactants and we end up with products. So here's my product here, but these are not my original reactants. So I need to start with them one at a time and make sure everything fits. Notice that this has got to be a positive and this has got to be a gas. That's two different things. This has to be a negative and this has to be a gas. It's already a gas. However, chlorine is a molecule and the chloride ion is a free ion. So we have to take care of that as well. And when we have all our equations written out, we're going to have to manipulate one so that Hess's law is fulfilled and they add up to be the overall balanced equation. You will either have to multiply by 2 or divide by 2 somewhere, almost every time. You can focus on the metal or the non-metal first. It doesn't matter. I picked the sodium metal to do first. We're starting off with the actual reactant, which is sodium solid. Now, we need to do two things. We need to make it from sodium solid to sodium gas, and then we have to make it from uncharged to charged. You really have to, by the definition, ionization needs to be in a gaseous state. So that's the first thing we do. Going from a solid sodium to a gaseous sodium is going to be heat of sublimation. That's going to the right across our heat curve, and therefore this is a positive value. The next thing we got to do is make that gaseous metal into a gaseous metal ion. For that to happen, sodium will lose an electron because it's a metal. By definition, When you have a gaseous metal losing an electron, this is called ionization energy. These are always positive. If we had calcium or magnesium, that becomes a 2 plus. We would need to do two of these, one for I1 and one for I2, because the energy values are different. The chlorine, well, down here at the bottom, we have the chlorine molecule, and here we have the chlorine ion. So we're going to add all these equations up to equal this bottom equation. And as you can see, there is no chloride ion in the final equation down here. So it must cancel. So on the right side, we are going to need a chloride ion that's in a gas form. So what do we need to do to the chlorine here to make it into the gaseous chloride? Well, we have to worry about things that are thermodynamically active. What makes something have a change in energy? Phases do, ionization does, one way or the other, whether it's electron affinity or ionization, and bonds do as well. So in this case, they're both gases, so that's not a problem. But you have to recognize what you start off with. You start off with a molecule of chlorine, and this is a covalent bond, which needs to go away. So that's our first step, is to make the covalent bond go away, and then we have to form the ion. So that's a two-step thermodynamic process. So first, I'm going to break that covalent bond. Up, I would call this bond energy, and I would find a chlorine-chlorine single bond and look that up. Bond energies are always positive. And a chlorine molecule contains two chlorines, so it's very important to make sure the coefficients work out. So to make a chloride ion, you have to add an electron, so I threw in the electron there. Now, everything should cancel out except a number that doesn't. So if you look at it, first of all, in terms of canceling, the chloride and the chloride will cancel. One's on the right, one's on the left. The chlorine and the chlorine will cancel. One's on the left, one's on the right. The electrons will cancel out. The sodium ion will cancel out. The gaseous sodium will cancel out. However, it doesn't really work that well because look at this. We have a chlorine molecule. How many do we have here? We have one. And how many do we have down here? We have a half. So that doesn't work out. Also, I canceled out incorrectly two chlorines with one chlorine. You can't do that. It's got to be a 1-to-1 or 2-to-2 or 3-to-3. So let's start over again. This guy right here needs to be multiplied by 1/2. Doing that, they'll actually cancel out correctly in the correct number. But in order, if I multiply this by 1/2, which is the same thing as dividing by 2, I got to divide this value by 2, which I did in red here. So if you remember doing Hess's law, you can either, if you flip-flop it, you change the sign. If you multiply or divide, you multiply or divide the delta H as well. These values will be given to you if they want you to actually solve for it. So now let's see if it all cancels out. The chloride, one of them, the chlorine one, the one electron, the one sodium gaseous ion with the one sodium gaseous ion, the sodium gas atom cancels out, leaving you with a sodium solid, a half a chlorine molecule, and a sodium chloride. And therefore, these add up to be this guy. So these will add up to be the delta H of formation. Delta H of formation is going to be a negative value overall. Because when you put these into an ionic crystal, it's a very strong compound, and therefore it's going to be a negative value, very stable. The reason why they call this a Born Haber cycle is because mathematically you can draw this thing like a cycle. I don't think this is nearly as clear as Hess's law, but you can see it goes around in a cycle. So if you're going up, this is all going to be y-axis stuff. There's really nothing on the x in terms of going left to right. And if you're going up, this is going to be energy values. So if you're going up, it's endothermic. If you're going down, it's exothermic. And so they do this in a cycle. To me, it's really quite confusing, but that's how they come up with it. Let's try another one. We are using potassium and oxygen gas. Now, they're going to give you either an alkali or alkaline metal. They're going to give you either a group 17 halogen or a group 16 oxygen of sulfur. That's all they're going to give you. We need to write down the equation for lattice energy. Remember, the equation for lattice energy would be the gaseous ions going to a single mole of ionic compound. Wrote down the gaseous ions hooking up to form the 1 mole of the ionic compound. This is lattice energy, highly negative. All right, so now these have to cancel. We have to start with what we have in the final thing. Potassium needs to change phase and change charge. That's two things, that's two equations. The oxygen needs to break the molecule, and the gases are the same, so the phases are the same. The charge has to be a two-step process because we have two electrons being added on. Those are going to be different energy values. So I put in here the first step would be changing the solid potassium to gaseous potassium. Heat of sublimation, a positive value as we stated earlier. Then we're going to get the gaseous potassium and ionize it. That's going to be ionization. If we had a magnesium or a calcium, we would have to do the ionization step twice. I'll give you an example here. Up top here, this is what you would do if you had some kind of metal that had multiple electrons taken off of it. I1 would be a positive value, and I2 would be a greater positive value. But you have to do a two-step process because this is thermodynamics, and each one of these would be a different value. We're not doing magnesium, so I'm going to erase this and go back to where we were. I like to deal with the oxygen. Everything's a little bit different depending on what group it's in. So oxygen is going to be a molecule, so we have to break the covalent bond, and then we have to add an electron to it to make it negative, and then we have to add a second electron to it to make it a -2. So that's breaking the bond, making it negative, making it -2. That's 3 steps. The first step with the oxygen is to break the double bond in the oxygen. That's going to be bond energy. And just like last time, we're going to need one of the oxygen ions. So we're going to change the coefficient to 1/2. Because if you break one, the definition of bond energy is breaking 1 mole of bonds. That would form 2 oxygens. We need 1. So we put the half coefficient in front. And then over here, for the bond energy, we're going to divide it by 2. Now, the first one is going to be the electron affinity 1, and that's going to be a negative value. And the electron affinity 2 is actually going to be a positive value because you're pushing a negative ion, a negative electron, onto a negative oxygen atom. The two negatives are going to repel. Now, once you get it in place, it will be a stable position, but the actual sticking the electron on is going to be difficult to do and therefore a positive value. Okay, if you look at this, everything cancels out. So you can go through it one by one to make sure the coefficients also cancel out. So you have oxygen gas with oxygen gas. Oxygen -1, oxygen -1. Oxygen -2, oxygen -2. You have 1, 2 electrons, and this needs to be 2 over here. So I do have to change this. This needs to be a 2. That needs to be a 2. That needs to be a 2. That needs to be a 2, and that needs to be a 2. In doing so, we have to multiply this number right here by 2 and multiply this number by 2. So I didn't do a very good job of taking care of the coefficients early on. So now the 2 electrons will cancel with 1, 2 electrons. The 2 potassium gas, 2 potassium gas, the 2 potassium ions, 2 potassium ions, and you're left with 1/2 oxygen molecule gas, 2 potassium solids, and a potassium solid on the right. This will add up to be the heat of formation down here if we had the values. The actual manipulating the numbers at the end is not a big deal. It's recognizing that we have these changes, divide by 2, multiply by 2, multiply by 2. Understanding the sign for each of these is going to be important too. That's something you have to just know.